All right. Hi, everyone. My name is Marta. I'm a software engineer on a Stellar core team, and today I'm here to talk to you about scalability, and specifically what we've built and where we headed. Cool. So before diving into details, let's kind of quickly go over some of our core scaling principles that guide our work and explain why scalability is so important. So our goal is to stay ahead of the network demands. Today, validators enforce strict caps on the total number of transactions that can be included in a ledger. And once traffic hits those caps, the system starts throttling incoming transactions. The reason we need these limits in the first place is to ensure that the network remains healthy under high load and doesn't choke and basically can continue processing transactions safely. When these limits are reached, something that we call surge pricing kicks in. So surge pricing is the process when users begin bidding higher fees in order to get into the ledger. Transactions that don't bid high enough fees either get dropped or arbitrarily delayed. So either way, it's not a great user experience because users have to either pay more fees or have their transactions dropped, and so they can't get into the ledger at all. So a scalability goal is exactly that. Give the network more room to process these transactions, stay consistently ahead of the demand, and keep the user experience smooth. So our second principle is around embracing openness and transparency. So last year, we started publishing our theoretical throughput results openly for each Stellar Core release. Specifically, for all this performance work that we do, we're now openly publishing not only the results, but also the methodology that we use to achieve these results. In addition, we publish exact steps to reproduce, as well as the infrastructure, like the test bed that we use to run these tests. So anybody out there can look it up and run the tests as well. And last but not least, we want to iterate carefully, but make progress continuously. So Stellar Core is a 10-year-old code base, and making these massive performance changes to it is kind of like performing an open heart surgery. There are tons of moving parts, and precision is super, super important. So rolling out these massive changes in production is always actually quite a challenge. So the balance that we aim for is move fast enough to keep improving, but careful enough not to break the network that's been running in production for over a decade now. Okay, so with that, let's briefly discuss where we left off last year. So last year, a colleague of mine, Siddharth, gave a talk also on scalability, where he presented a couple of initiatives that we were going to do. So let's see where we are today. Before we do that, though, let's start by zooming out a little bit and looking at the three main functions of Stellar Core. And the reason this is important is, so we're working on optimizations in each of these areas. So seeing the high-level picture of all the things that Stellar Core is doing will really help us better understand the changes that we're making. And you can think of these as like stages that a transaction goes through before it is considered final. So our first stage is dissemination. So the Stellar network consists of around 600 nodes, and all these nodes participate in disseminating new transactions that continuously enter the network. This is really important because these new transactions need to reach validating nodes so that these validating nodes can include the transactions in the blocks that are going to be confirmed. So essentially, dissemination is responsible for that process. Our second step is consensus. Here's where validator nodes actually agree on the next block using the Stellar consensus protocol. Together, they decide which transactions should be included in the next block. And by the way, the transactions that they use, they receive from the previous stage, from the dissemination stage. Once consensus is done and the next block is determined, nodes enter the phase that we call execution phase. So that actually means committing transactions to the database. This is where we actually observe changes to the blockchain. So maybe accounts get credited, accounts get debited, some offers get crossed, all that good stuff. But once that stage, the execution stage completes, your transaction is considered final. So last year at Meridian, we presented to you a couple of initiatives that we planned to do on the scaling front. Our biggest theme for 2025 was parallelism. So our goal was to transition from Stellar Core's historically single-threaded processing to a multi-threaded approach. To achieve this, we focused on introducing background processing for transactions, shifting most of the transaction processing of the main thread into the background. And similarly, we aimed to move the execution phase into the background. Finally, as Soroban scales, we prioritized parallel processing of Soroban transactions, ensuring that they could execute not only in the background, but also concurrently with each other. So I wanted to quickly go over where we are today. So we rolled out the background transaction dissemination to mainnet, which pushed things like networking, hashing, decoding, authentication of the main thread into the background. There was a nice side effect of this project. It actually forced us to build a multi-threaded infrastructure for Stellar Core. And you can kind of think of it as like Rails to do work in the background. Once the Rails were in place, we could start doing even more things of the main thread in the background in a more streamlined way. So for example, we added transaction traffic deduplication and then signature verification for transactions. And then the end result is that the main thread has a lot less work to do, and consensus can run faster. We also introduced background block execution, which allows the main thread to continue disseminating transactions and votes while execution is happening. So that feature is already supported in Stellar Core. It is currently opt-in, so it's enabled on select nodes, but we plan to enable it on by default. And last but not least, Garant already spoke earlier about advancements in Soroban execution, and specifically in parallel Soroban execution. But just to quickly reiterate, parallel Soroban execution is already supported in WISC protocol on mainnet today, with the actual parallelism parameters, like the number of threads to execute the transactions on, to be determined by the governing validators. But that's not all. Lots of other important work happened behind the scenes that is actually quite critical to our scalability goals. For example, we added a lot of aggressive caching of ledger state, as well as validation results of blocks. We've also addressed a ton of tech debt. So while this might sound kind of tangential to the topic of scalability, we actually realized that a lot of these tech debt items were preventing us from measuring like the true impact of the big performance changes that we were making. So as part of this, we've revisited the benchmarking framework itself, as well as the synthetic load generation module that we use to run these tests. We're also currently looking into improving our testbed infrastructure. So we've also done many experiments on all fronts, in the transport area, scheduling, block propagation, and so forth. And these experiments is not something that you will see in our release notes, and the impact of these experiments is not always visible, because it might not even be in our public repo, because a lot of them are private. And of course, some of these experiments are failed, which makes us really sad. But I think the bigger picture to see here is that these really help us build a high-level picture of performance bottlenecks in our system, and figure out the highest impact areas to prioritize next. So I also want to emphasize that this was a really big team effort, and lots of folks on the Stellar Core team contributed to this. So Garant, who spoke earlier, right before me, a colleague of mine, Brett, who's not here this year, they all contributed, so this is all very exciting. Okay, so with that, how do we actually measure our theoretical throughput? This is one thing we kind of realized we don't talk enough about publicly. And we did say in our scalability principles that we want to be open and transparent about the process, so here's the process. So we have this theoretical maximum throughput test, and its goal is to showcase Stellar's theoretical throughput capabilities. You can kind of think of it as like finding the system's upper bound. To do this, we use Supercluster. So Supercluster is this awesome open source tool that can be used to run network simulations and load tests. For this test, we use a simple network of 7 nodes, and each node is given fairly modest resources, so only 4 CPUs and 6 gigabytes of RAM per node. And this is kind of on purpose. Like we specifically didn't use the best hardware possible because we still want to be able to like identify and study bottlenecks that are relevant to our mainnet today. And nodes on mainnet run fairly modest hardware. So in this test, we create artificial load using the built-in load generator that already exists in Stellar Core. And to find the maximum throughput, we use binary search. An iteration of binary search passes if the system can sustain the desired throughput for about 20 minutes. And 20 minutes is a bit of a little bit arbitrary here. We just want to balance like a realistic sustained load scenario with just the simulation running time, because otherwise these tests take very long time to run. An iteration of binary search fails if basically anything weird happens during the run. Maybe a transaction gets dropped, or a node goes out of sync, or the system is slow. If anything like that happens, basically the run is going to fail. For our payload, we use simple payments. And of course, now that Soroban is such an integral part of the network, we want to add support for Soroban and start publishing those results as well. And by the way, note, because this is classic payments, the impact of parallel Soroban is not yet observable in this test. But our plan is to add support for it as well, so we can see the impact. And for this test, we also enable all opt-in performance features. So how in the previous slide we said that we're still rolling some out on mainnet, but for this particular test, we just enable everything. I also wanted to note that this is an end-to-end system testing, and that includes all the stages that we just talked about earlier. So the dissemination stage, consensus, execution. This is different from the execution engine testing that Garen spoke about earlier in his previous talk. So this is a full end-to-end testing. So let's take a quick look over the throughput, about the throughput revolution in 2025. So we saw a really promising trajectory with our theoretical throughput results. Specifically, we released the version 22.3.0 of Stellar Core, which nearly doubled our throughput. And we saw a nice positive trajectory since. We're currently working on our next performance-oriented release, version 23.1.0. Which is also showing some preliminary promising results with the throughput going past 2400. Of course, this is still an early build, and we need to make sure that these changes are sound before we release them, but we feel good enough about them so far to share these results with everyone. Great, so where do we go from here? Let's actually spend some time talking about this next scalability project that we're currently experimenting with. But first, to understand what we're doing, we actually need to go on a little tangent here. So when I was putting together this talk, I kept thinking, what would be a good analogy to describe this project best? But then I realized, so this analogy actually already exists. If you've ever taken a computer architecture class, you might have even seen it before. It's exactly the same playbook that CPU processors use to squeeze out more instructions per unit of time. Enter the laundry problem. I promise this is going to come back to blockchain scalability, but for now, imagine we have 4 loads of laundry that we need to do in one evening. From the equipment, we have 1 washer and 1 dryer, and then in terms of time commitment, it takes 20 minutes to wash, 40 minutes to dry, and 30 minutes to fold. So let's say we do our laundry sequentially. Our x-axis is time, and our y-axis is the load that we're currently doing. We start the washer at 8, the dryer at 8:20. At 9 p.m. we start folding, and then at 9:30 we're done folding, so we can load the next wash, and then continue with each subsequent load. And we continue with all 4 and finish our laundry at 2 a.m. There's an interesting observation here, though. I can guarantee you that nobody in the world does laundry this way. Each stage of the process is idle most of the time. Why wait for the dryer and the folding to be done before starting the next washer? So if you've ever done laundry, you've probably done something more like this. So this approach is called pipelining. if we were trying to minimize the time that each phase is idle, we try to start the next stage as soon as possible. With this approach, we actually finish our laundry at 11:30 p.m. instead of 2 a.m. So we actually end up reducing the total time to do 4 loads of laundry from 3.5 hours, from 6 hours to 3.5 hours. That's a 42% reduction in the total amount of time to do 4 loads of laundry. And if we were to look at it via a throughput angle, before we could only do 1 load of laundry per 90 minutes, whereas now, in the same 90 minutes, we can, of course, still do that 1 full load, but we can also do 2 full washes and almost 1 full dry, only short of 10 minutes. That's 1.77 loads per 90 minutes, or a 77% increase in our throughput. Okay, so what does it actually have to do with Stellar Core? Let's try to sketch how this approach might look like for Stellar Core. First, let's figure out what our loads are. So our loads are essentially ledgers. Reminder that the ledger is a state of the blockchain after a set of transactions agreed on by consensus was executed. As time goes by, the network produces new ledgers, and then this process repeats every 5 seconds. Instead of washing and drying, that's our consensus. The process where nodes on the network agree on the next block to be confirmed on the blockchain. And then finally, folding is our execution. After consensus is done, all nodes know exactly the transactions that will be committed to the ledger, so they can execute those transactions. So going back to our realization about laundry, while washer is running, the dryer is idle, and then while dryer is drying, the washer is idle. So I hope you see where I'm going with this. We can actually use this pipelining approach to pipelining consensus and execution such that whenever we execute the ledger, we can start consensus for the next block. Well, what does it actually mean for our system? Well, first, pipelining keeps CPU and networking resources fully utilized. The duration of each stage is unchanged, but our throughput increases. Also, with pipelining, throughput is now bottlenecked by the slowest stage, in this case, consensus or execution. And I also wanted to point out that this technique is the most effective when transactions have little to no conflicts. And specifically, because consensus for the next ledger begins while execution for the previous ledger is still happening, it is possible that the results of that execution may invalidate some of the transactions that are included in the next block by consensus. So minimal conflicts are important for maximizing chances of transactions succeeding, for transactions included in blocks succeeding. So pipelining also allows increasing throughput while keeping end-to-end latency the same. Actually, in our 2025 roadmap, we outlined our goal to reach 2.5 second block time. Today, block time is 5 seconds, and it's essentially the sum of consensus and execution, which means that both stages run one after the other. With pipelining, the block time is no longer additive. It becomes whichever stage is slower. Right now on mainnet, both stages run well under 2.5 seconds, so we feel good about the 2.5 second target. So in practice, as we plan to move towards the 2.5 second block time with pipelining, that means that the end-to-end latency remains unchanged because the users still need to basically wait for the execution to be done in order to consider the transaction final. But our throughput increase basically doubled with this approach. And by the way, if you're interested in learning more about how we plan to decrease that end-to-end latency, you should stick around for the next talk because our CTO, Nico, is going to talk about exactly that. Okay, and we actually have already done some preliminary work on this and put together some prototypes. This is, of course, still experimental, and we're still working through some of the bottlenecks that I've talked about earlier. But the results already look pretty promising. The idea here is that we just want to get a sense of the performance benefits with classic payments for reference. But the number that we were able to get was the 3,300 transactions per second. This is really just the beginning, with more to come. But for now, that's all I have. Thank you very much.
Okay. Oh. Thanks, Marta. Thank you so much.